we are concerned with finding the area bounded underneath the curve between the curve and the x-axis, correct? So I'm going to mark this, and I'm going to call this point A, and I'll call this point X. I'm actually not going to look at the area bounded from A to X, but I'm going to look at the area bounded between X and X plus H. What is the width between X and X plus H? It is H. This is the area that we are referring to. So I would like to use notation that's a little bit new to you, but you'll make sense. The area bounded from X to X plus H is equal to, I'm going to write two other areas that we can use in order to find the area from X to X plus H. And the first area is the area from A to X plus H. What do I have to subtract off of that larger area then to leave me with this red space? A to X. Very good. Is everybody okay with that statement? Then what I'm going to do is I'm going to insert something that's approximate. We're going to leave the right side alone, but I'm going to change the left side a little bit. What we've been doing in order to approximate area is we've been drawing rectangles, correct? So this area could be approximated by the green rectangle. Fair enough? All right. So in order to find the area of that rectangle, I will take the width, which is H, times, at what point do I evaluate the height of that rectangle? At X. And Sean, how do I get the height? What do I do with the X? You plug it into the function and you get f of X. So that green rectangle is approximately equal to the area that I want as a whole. I'm going to do something a little bit different here. I'm going to divide by H, and I get f of X is approximately equal to the area from A to X plus H minus the area from A to X all over H. And finally, I'm going to do one more thing. See right now that I have an underestimation with my area? Would you agree that as I draw X plus H closer to X, that underestimation will become smaller and smaller? And that they will become more like one another? Well, I want to draw those closer together. How can I draw those closer together? Take the limit as H goes to 0. So then all of a sudden the function becomes the same as the limit as H goes to 0 of the area from A to X plus H minus the area from A to X all over H. What time does lunch happen? Okay, so we're actually going to get this in. This is amazing, but we don't know what we're looking at. This is what I'm going to uncover for you right now so you know what you're looking at. This is the big part. This is what you really have to follow. Does this look familiar? F prime of X is equal to the limit as H goes to 0 of f of X plus H minus f of X all over H. Give me a function you know the derivative of. 3x squared, great. F of X is 3x squared. So if we write the limit as H goes to 0 of 3 times X plus H, quantity squared, minus 3x squared, all over h, that's equal to, what is that limit equal to? 6x. That's the derivative. We used to work those all the way out, right? We don't need to work it out right now because we know it ends up being 6x. Give me another one you know the derivative of. How about the root of x? The limit as h goes to 0 of the root of x plus h minus the root of x all over h, what will you get? 1 over 2 roots of x. I'll do one more. What about sine of x? The limit as h goes to 0 of arc sine of x plus h minus arc sine all over h is equal to, do you remember what it is? 1 over the root of 1 minus x squared. So what does that mean? The derivative of the function, the derivative of this is right here, right? Connect that with this, and you'll see it. The derivative of this is this. The derivative of the area function is the stinking function. The derivative of the area function is f of x. So there's a relationship between the actual function and the area. So I'm going to flip it around. If the derivative of the area function is f of x, then the antiderivative of f of x is the area function. So your question is, what the heck is an antiderivative? You do it backwards. For example, if f of x is 3x squared, what is f prime of x? What is big f of x, or the antiderivative? What would you take the derivative of to get 3x squared? X to the third. So we're used to going this way, right? We now want to go that way. That's an antiderivative. So it's not the antiderivative, it's an antiderivative. There's an infinite number of them. So the antiderivative for a function, okay, if you have f of x is equal to x to the nth, then f prime, okay, we'll pick it up when you get back. All right, so I'll get off my high horse here and we'll do this. If I have f of x is equal to x to the nth, then the derivative we've said is n times x to the n minus 1. But if you want the antiderivative, which we'll call big f of x, the antiderivative, or where that comes from, okay, is x. We have to raise the exponent by 1 and divide by that new exponent. That's the power rule for an antiderivative. So once we practice finding the antiderivatives, we can apply it to our area formula. So find an antiderivative for the following. Big F in this situation would be x to the fourth over 4. Yep. And it's easy to check. If you're wondering if it's correct, take the derivative, and you should get x to the third. The next one, 5x to the fifth over 5. 5's cancel, we get x to the fifth is our antiderivative. If you take the derivative of x to the fifth, you get 5x to the fourth? Yes, you do. 4x to the 6th. What's the antiderivative? And antiderivative. Yep. So Darren caught me with a little bit of a lie earlier. I want to be clear. This is an antiderivative. It's not the only one. If I simply just added 1 on the end there, if I take the derivative of this, do I get that? Yeah. If I added 10, do I still get that? So there's an infinite number of antiderivatives. This is one of them. Okay. We'll talk about that constant piece later on, but right now, for the sake of this piece, we don't introduce that yet. That will be for next chapter. So sometimes you might have to rewrite it. 3 over 2, x to the negative 3. And once I rewrite it, I can now take an appropriate antiderivative. So big F of x would be equal to 3 over 2, x to the negative 2 divided by negative 2 over 1. So multiply by the reciprocal, and you can see you'll get negative 3 over 4x squared should be your result. Okay, that brings us to the fundamental theorem of calculus part 2. Part 1 is different. It's a little bit strange to most people. Fundamental theorem part 2 directly relates to what we have just done in our previous examples of days. Past 3 days we've been doing this. The integral from a to b of f of x dx. We've been evaluating that, and we evaluated it by using the limit of Riemann sums. Now, instead of doing that, you can do this. You find an antiderivative, and you plug in b. Then, that same antiderivative, you plug in a. And you subtract the 2. If I could show you real quick why you subtract the 2. These are sometimes things I just hope you figure out on your own, but I'll show you. Say that this is A, say that this is B. When you do f of B, it gives you all of that. But we don't want all of that, so we have to subtract off f of A, which is this part, and that's why it leaves you with just the blue part. That's graphically what's happening. Okay? See that? All right. Let's go to work. After we have one more piece to put down here where f is any antiderivative of f. So big F is any antiderivative of little f. So could you attach a constant? Yes. It would just be a little bit more work, but you could. What you will do on your assignment today is identical to this. Only you will also sketch a small graph. X squared looks like this, and from 0 to 2, I'm looking at that area. So should it be positive or negative? It will be positive. What is an antiderivative of x squared? The way we then show that we evaluate it at 2 and 0 is we draw a vertical bar. We put 2 at the top and a 0 at the bottom. I'm embarrassed to say that I don't think I've ever been told what that bar is actually called. I should probably look it up and figure it out. The Tanner bar? Okay. Gens bar. Okay. Limbo bar. Oh my goodness. Okay. So 8 over 3 minus 0 over 3 is in fact 8 over 3. So you remember the work that we did the other day in order to find the area. We used the infinite limit of Riemann sums. No more. Fundamental theorem of calculus says find an antiderivative and plug them both in. Well, okay, so it's not uncommon, but the other way, you were doing calculus. You were calculating the infinite and the infinitesimal. Here, you're using the results of the calculus in order to evaluate. So the antiderivative of 3x squared, x to the third, evaluated at 4 and 2. Talk about area happening quickly. Wow. 3 roots of x. What does that graph look like? Something like that, right? Moving from 1 to 2. So we're looking at that area right there. I'm going to rewrite this as 3x to the 1/2. Give me an antiderivative. 3x to the 3/2 divided by that 3/2. Instead of dividing by 3/2, I multiply by 2/3. So the 3's will cancel. I get 2x to the 3/2 evaluated at 1 and 2. I plug in 2. You have to plug in the top number first. 2 to the third. 8 square root. Square root of 8 is 2 roots of 2 times 2. 4 roots of 2. Plug in 1. You get 2. Now, to my friends Sarah and Sarah, who say that they like the previous one better, that is my question to you. Do you have a sum for the square root of x? We have power formulas. We don't have a sum or we don't have a square root formula, do we? Do we have a sine formula? No. So that's why calculus allows us to do some of those things pretty nicely then. So. All right, this one. The graph, you would have to look at this one on your calculator, but it looks something like that, where this is at -3. This is a little bit past 1. This is the kind of area we're looking for. So that could be positive or negative. It's going to be negative. If it's below the x-axis, it's negative. Antiderivative of x to the third. X to the fourth over 4 minus x to the third over 3 plus minus evaluated at right, 2x squared over 2, very good. That's why I get the x squared. And the 3, it's 3x to the 0. Raise the 0 to 1, and you get 3x to the first over 1, which is 3x. All right, so we plug in 1, we get 1/4 minus 1/3 plus 1 minus 3. Common denominator would be 12. So 3 over 12 minus 4 over 12 minus 24 over 12 is negative 25 over 12. Again, I hope you could appreciate that these 4 terms, if we were to do it doing what we did yesterday, that would take us quite a while. And although you're very good at it, a much higher probability of making a mistake. So our last 2 examples. Sine of x. What is the period of sine? 2 pi, once around the unit circle. So this is the graph of sine. We're looking at it from 0 to pi. Again, you have to make a quick sketch on your assignment today. So I just want you to understand graphically. I've always assumed that everybody can picture the graphs, and I know I'm wrong in that. So you're going to be, yes, you're going to be much better if you could just quickly sketch a graph. So I need to know the antiderivative of sine. Negative cosine, how'd you come up with that? So last hour and every year, I just outline it for students so they could kind of get it through their heads. We have sine of x, we have cosine of x, we have negative sine of x, and we have negative cosine of x. What's the derivative of sine? Derivative cosine, derivative negative sine, and derivative of negative cosine. So now that we found the derivatives, now you could say, well, I'm going to count this as f and this as big F. Okay, so the derivative of big F is little f, and the antiderivative of little f is big F. So that tells us that the antiderivative of sine is negative cosine. So if you can't remember it, make yourself a chart and continue to think through that until you can kind of figure it out. Everybody good with that? So antiderivative of sine is negative cosine of x. We evaluate it at pi and at 0. Oh, looks like a little trig. Good thing that we remember all of our trig. I have my terminal points. What's the terminal point at right there? Negative 1, 0. Terminal point here. Oh, 1, 0. So what's the cosine of pi? Negative 1, make it negative 1. Minus, what's the cosine of 0? 1. Make it negative. Turns out that that exact area is 2. Last example. This graph, 2 over x squared, looks like this. Do you think we could do it from negative 1 to 5? No, it's discontinuous. It has to be continuous, okay? And so from 1 to 5, the area is going to look like that. Should be positive. This is 2x to the negative 2. What is the antiderivative? Negative 2 over x. Very good. So I take negative 2 over x, and I evaluate it at 5 and 1. Plug in the 5, negative 2 over 5. Minus, what do you get when you plug in 1? Negative 2, so plus 2. Or negative 2 over 5 plus 10 over 5 is 8 over 5. There you have it. You do not learn anything new tomorrow. You have a worksheet in class tomorrow on this topic. So you'll have all hour to work on it. I'm going to give you a sheet right now to practice this.